afternoon, everybody. I'm uploading this at a different time. Welcome to End of Mission, the podcast where we talk about space missions that have ended. I'm Pavel, the Slav Squat cosmonaut, and who are you, Tovarish?
I am not an American spy. Duh.
Okay, someone's going to the gulag.
Please don't send me there.
Nope, you're going to the gulag now, comrade.
Dang it.
Comrade.
Was it because I was Slav squatting on my toes?
Exactly.
Dang it.
We listened to some hard bass before this. Get ourselves in the mood.
This man needs Slav squat on television.
Okay, by watching hard bass, we watched some Life of Boris, okay? Sue me. Please,
Sue Boris?
Please don't sue
No,
me.
don't sue Boris.
Please don't sue me. Yeah, don't sue him. He's in the... Yeah.
Don't sue anyone.
Unless they deserve it.
Unless their name's Sue. Then you can sue them.
Yeah. No, that's what they're doing. They're being a sue, so that everything they do is a sue.
Oh, okay.
Isn't language funny? Today we're talking about two spacecraft, actually, but it's one mission because it's easier to do it this way. I'm gesturing wildly with my hands. It's called Vega. What do you think it's about?
I think it's about slingshotting satellites around lemons by the art.
Oh, okay. What about this art over here? You see this art?
I didn't even notice that
Oh my
one with its
goodness.
bright, flashy colors.
Yeah.
I was focusing on the dull gray graphics. But okay, yeah, looking at this. Let's see. It says a landing site. And it drifts 46 hours. Hemisphere released. Balloon envelope unfolds and inflates. I have no idea.
Yeah.
I have no idea.
Well, we're talking about the last Soviet missions to Venus.
Ooh, okay.
Yeah. And it's got balloons.
Balloons on Venus.
Yeah.
Huh.
All right.
Wacky.
So what? You're going to say something?
I was going to say wacky. That's
Yeah.
wacky.
Oh, that's wacky. Yeah. Or whack, I think is the modern term.
That's whack.
Yes. So Venus, it's the second planet from the sun. Its radius is 6,051.8 kilometers. It's about 3,760.4 miles. So it's like 95% of Earth's.
So it's like the same size as Earth. Okay.
Yeah, it's a little bit smaller. The surface gravity is 90.4% G, so I'll only weigh 200 pounds. And you'll weigh...
Instead of 220?
Yeah, whatever. Fun fact, it's actually rounder than Earth.
Really?
Well, because Earth's flat, right?
Oh, right.
It's,
yeah, that
it's
makes
rounder
sense.
because it's upside down and doesn't spin fast.
Oh,
Yeah.
okay. So it can preserve its spherical shape.
Real planets have curves.
Real planets have curves.
Yeah,
Earth is not a planet. It's flat.
that's true. Yeah, this is in the firmament, actually.
Ah, right. Okay.
Yeah.
Yeah, that makes sense.
That's what the diagram's for. So the axial tilt is 177.36 degrees, so it's upside down.
With 180 being perfectly upside down.
Yes.
Okay.
Earth is what, 24.3?
23.5.
Whatever. Mars is
It makes a bit of a difference.
Mars is the other one, I think. I don't
Yeah,
remember.
yeah. Mars is the other one.
I don't care. But I should care.
You should care.
So its day length is minus 116.75 Earth days. That doesn't mean you time travel on Venus. It just means that the planet spins backwards.
But that doesn't equate to time travel?
No.
Dang it. Superman lied to me.
Yeah, I'm sorry. Well, Superman was going a lot faster.
Yeah, but he was spinning the Earth the other way around.
Yeah,
right?
but he was going really fast to do that.
Right, but the Earth was going backwards.
No, it was an optical thing because he was traveling fast. Okay, we're not talking about Superman. So Venus's year is 61.52% Earth years. So it's like 200 something days.
Okay.
Or 1.92 Venusian days.
So Venus spins like twice in the
Yeah.
same time that it orbits
Because it's upside down
the sun.
and slow.
Right.
Yeah, again, that's why it's rounder than Earth. Because Earth is flattened a little bit because it spins. You ever see
Right.
pictures?
And because
Jupiter's actually noticeably flat.
Oh yeah, yeah,
Yeah. If you ever see a
Saturn
picture of it,
is even way flatter than,
Yeah.
than Jupiter. Yeah,
because you ever see a picture of Jupiter where it's perfectly round, it looks wrong.
yeah.
It's
Yeah,
weird.
it's like, that's weird, right?
Yeah, it is.
Because I've taken astronomy images of Jupiter, and sure, it looks like a white blob, but it's a deflated white blob.
Yeah. So the semi-major axis, so that's its orbit, is 72.3% of an AU. So it's that's in the inside of Earth's orbit.
What's an AU?
Astronomical units, about 93 million miles. It's the distance from the Earth to the Sun on average.
Oh, okay, so 1 AU is Earth's orbit.
Yeah. I mean, technically it's the semi-major axis because Earth has a slightly eccentric orbit. But it's the average.
Okay,
93 million miles. Just keep that in the back of your head.
got it.
I don't know how many kilometers that is because I'm in America. Okay?
150 million kilometers.
That sounds about right.
Yeah.
So the surface temperature is a balmy 464 degrees centigrade or 867 degrees Fahrenheit. So that's like your place.
That's warm. That's
Yeah.
toasty.
It's like Arizona.
That's almost as hot as Arizona.
Yeah.
So,
Surface pressure on average is 92 atmospheres. So it's 92 times the pressure as here on Earth.
jeez.
Yeah.
Okay, so that's like what, the bottom of a swimming pool,
At least.
at least.
Yeah.
Okay.
Yeah, your ears will really hurt. Because mine do whenever I go in the swimming pool.
Okay. Maybe mine won't as much, but
That's true. All right, so here's some historical background. Venus, of course, is the morning and evening star. That's when you see it the best. It's the brightest. Venus was named for the goddess of beauty and love. Also, some other form of expressing love, but I'm not going to name that because this is PG.
okay.
So, unfortunately for the ancient astronomers, the burning passion they felt for Venus was actually a manifestation of the superheated nightmare.
What?
Burning heat passion for it, passionate heat, burning passion. I wrote this late at night, okay?
Okay.
So the astronomers thought it was a beautiful planet. It's hot. They were kind of right.
Yeah, I mean, yeah, it
It's
definitely
hot.
is hot.
Not because it's some hot chick. It's just hot.
It's over 800 degrees.
Yeah. It's pretty toasty. It's on that, like the crazy matrix, the crazy scale, hot and crazy, right?
Yeah, the hot, crazy
Yeah.
matrix, yeah.
So Venus is really hot, also really crazy because of it.
Got it.
Yeah.
Got it. Okay.
So insert failed relationship joke here, if you've got one.
I think we just got one.
Yeah, because of how similar it is to Earth, Venus, of course, has been the subject of a lot of interest in science and science fiction. A lot of science fiction has portrayed Venus as this steaming jungle planet.
Mm-hmm.
It's not. It's volcanic nightmare.
So it's Hawaii.
It's Hawaii in the volcano, yes.
Ah, okay.
Yeah.
Got it.
Much like the other two other inner planets, Venus has been the target of interplanetary missions because it's really easy to get to. I think the window for Hominid transfers is like once every 10 months.
Really?
Yeah. Versus Mars, which is once every 24.
I thought it was 26.
Yeah, 26. That's... God.
Yeah, so over 2 years. So it's over 2 years to get to Mars, but
Yeah.
every less than a year to get to Venus for the transfer windows.
Yeah. So you can do it, once a year. And for going to places like Jupiter or the outer planets, it's about once a year, roughly.
Okay,
These
so
usually fly by
Mars is
Jupiter.
just hard to get to.
Mars
is what you're
sucks in that regard.
saying. Okay.
So it's really easy to access, and it's really good for gravity assists. We'll actually talk about that when we talk about Galileo.
Okay.
Because
it's big.
Yeah, it's big compared to Mercury or Mars, which aren't.
Right.
Also, Mercury's just hard to get to in the first place.
Okay.
So, obviously, the Soviets did a lot of Venus exploration. And this is a list of every Soviet mission to Venus, and then ours at the very bottom.
Okay. So when so 1 through 27 is the Soviet missions,
Yes.
and then ours is 1 through 5.
Here's a hammer and sickle. These are the Soviets.
Is that backwards?
No, it's the correct way.
Okay.
I'll draw it differently next time. Okay.
Thank you.
So the first mission to Venus ever was in February 1961. It was 1VA number 1. And the upper stage did not ignite to burn it on a interplanetary injection.
Oh.
Yep. Then there was Venera 1. Also, they always launch these in pairs. We did this too.
Okay.
The Soviets kept doing it. We stopped.
Okay.
So there's Venera 1, which was launched in February 1961. It flew by Venus,
Oh.
except the communication system failed.
Oh.
so it doesn't count.
So they privatized the mission.
Yeah, it's like they're like 10 days out, and the communication system failed.
Whoopsies.
Yeah, and then you have a series of they didn't. So one of the things about Soviet numbering and naming schemes was, if it didn't work, it didn't get a name.
Oh.
Or even a number. This is actually a big problem for the Apollo-Soyuz test project, because 2 missions before that, the one that we were working with them on, they had a failure where the second stage didn't separate after it lit up, so they had to do an abort, and the Soviets didn't number it.
Oh.
Yeah. This made NASA worry, because they said, you had a launch failure and didn't even acknowledge it, and they kind of, okay, fine, it's Soyuz 18A. That's why if you ever look at a list of these missions, I think it's 18A. Because then there was...
Okay.
Yeah, because they didn't count it. They never counted the ones that failed.
It didn't get to orbit. It doesn't count.
Yeah. It's a very... it's a different way of doing things.
It's very Soviet.
Very Soviet, yes. Okay, so you can see there's a lot of issues with these. So for the next 3, in 1962, the upper stages didn't work. So they made it to orbit, but they didn't turn back on to go with the interplanetary injections. Then there's 3 MV1. So these are also the name of like the satellite buses, because they weren't all identical. You can see pictures of the different ones. I didn't include them because we might talk about them one day.
Okay.
They evolved. So 3MV number 2 exploded. Cosmos 27, so that, Cosmos designator means it didn't work. March 1964, the upper stage failed. But finally, there was Zond 1, which is weird because the Zond missions usually went to the moon. So Zond 1 in April 1964, which, hey, it's Dad's birthday, did a flyby of Venus, but the electronics failed, so it doesn't really count.
Gosh, dang it.
Yep. Then there was Venera 2 in November 1965, which did a flyby, but then suffered a communications failure. And there was Venera number 3, also November 1965. This was actually an atmospheric entry probe. It also failed.
So it seems like if it reaches orbit, the upper stage doesn't work, or if the upper stage does work, the communications don't.
Again, that's really it's really funny to look at these lists of these different missions, especially in the 1960s. They'll launch, like in a 6 months period, right? We'll launch one, it'll explode, we'll fix the rocket, we'll launch again 6 months later. In that same time, the Soviets will have launched 6 missions, and they'll all have exploded differently. Right? Okay, so then there's Cosmos 96. It exploded. Then there was Venera 4 in June 1967. This is when they were launched, by the way. It took them a few months to get there. This did the first successful atmospheric entry of Venus.
Hey. Yeah. All right.
Then there was Cosmos 167, which had suffered an upper stage failure.
God.
So then there's Venera 5 and 6, which were atmospheric entry probes that survived 53 and 51 minutes in the atmosphere.
Whoa. Okay.
Yeah. And then there's Venera 7, launched in August 1970. It landed on the surface and then tipped over.
Oh. Dang.
Yeah.
That sucks.
Then there's Venera 8, launched... Oh, no, wait, I skipped one. Cosmos 359. It got stuck in low Earth orbit. I think that one actually re-entered the atmosphere a few months ago.
Oh.
Yeah, they've been up there for a while.
That recently came home.
Yeah. Or it was a few years ago. I can't remember. Time is weird now. Because I'm old.
Time is relative.
Yeah.
It's always been relative.
Like my cousins.
Yeah.
So then there's Venera 8, which landed on July 22nd, 1972.
Mm-hmm.
It landed, took samples, did science.
Yes!
Then there's Cosmos 482, which got stuck in low Earth orbit.
Ah, dang it.
So then, now we're to talk about the actual successful missions. The rest of these are actually successful, that we know of.
Okay.
Yeah. So, Venera 9, June 1975, was an orbiter and lander combination, and it returned images from the surface, like these.
Oh, dang.
Now,
okay.
For reference, these are colorized by a guy named Don Mitchell. But this is what the surface of Venus looks like. Because they actually had a color reference image that they used to calibrate the cameras. We do this in all of our space missions. So if you look at collections of images of these spacecraft, you'll find one where it's like, here's a block of different colors. This is to calibrate the camera. Yeah.
The color palette, okay.
Yeah, so that when they take pictures on the surface and they have that up, you can see the difference.
Right, so you could correct it.
Yeah. So it turned images like this. This, of course, has been they've all been kind of patched together, but it looks like looks like a nightmare.
Yeah, it looks like it looks like Arizona,
Yeah.
but yellower.
Yeah, Arizona with a haze.
Yeah.
Yeah.
The Mexico filter.
Oh yeah, yeah. So Venera, 9 and 10 were orbiters and landers. Venera 11 and 12 were also orbiter and landers, but they also suffered failures on the surface. They didn't last as long.
I mean, it is nice and toasty there, so I can imagine how.
I heard this story. I don't know how true it is, that the Soviets built a giant kiln to test their Venera landers. And during one of the tests, they looked away from it to talk to Vasily about something. They turned back and it was gone.
That sounds about right.
Yeah. Now the question is, was it because the lander just didn't exceed its lifetime, or is it just some Soviet technology just failed?
Yeah, both maybe.
It could have been that, yeah.
Yeah.
So Venera 13 and 14 were landers, and both of them recorded sounds on the surface. And I have linked the sound from Venera 14 in the description.
Oh,
It's,
awesome.
It sounds pretty windy. And then they have a drill out.
Okay.
It's really cool. Then Venera's 15 and 16, these were, June 1983. These were orbiters that did radar mapping. You know in Kerbal Space Program, there's that surface scanner antenna you can put on your spaceships? That's like a dish, but it's not like a round dish. It's like rectangular, like a banana.
Yeah, it's like the Pringles looking dish.
Yeah. That's modeled after these. That's what that's modeled after.
Okay.
Yeah, on top of the bus. So
Got it.
So now these missions, Vega 1 and 2, will be the last 2 Soviet missions to Venus. These will be 28 and 29. Now,
Okay.
in America, we have done, at this point, 6 missions to Venus. Mariner 1 launched on July 1962. It exploded.
When did it explode?
It was one of the early Atlas Centaur flights, I think.
Okay.
It was like 2 minutes into flight. I think the
okay.
Atlas failed.
Dang.
Then there's Mariner 2, launched in August 1962. It performed the first successful flyby of Venus.
Hey!
So, for perspective, this is where the Soviets were.
Still failing at the upper stage.
Yep. Then in June 1967, Mariner 5 did a successful flyby. That's where we are in the Soviet Union. Oh, so this is the time when they were actually landing in the atmosphere and working on that.
Okay.
Yeah. And then Mariner 10 launched in November 1973, did flybys of Venus on the way to Mercury. Actually, I think that's where this image comes from. Mariner 10.
Oh, okay. Yeah, makes sense.
And then at this point, 1978, we launched Pioneer Venus 1 and 2. So one of them was an orbiter, and the other one was a multi-probe. So it's the same bus, but one of them had little atmospheric entry probes on it.
Ah, okay.
Yeah, pretty cool.
Okay. Yeah, that sounds awesome.
And Pioneer Venus is active during this mission.
Got it. Okay.
So I want to talk about Halley's Comet. You've probably heard of this one, right?
Yeah, it's the famous one, the big one.
It's the big one. So its dimensions, so it's a bit smaller than Venus. It's only 15 by 8 kilometers, and I forgot to convert it to miles. So that's like 10 miles by 5.
5, yeah.
Yeah.
10 by 5.
10 by 5. Kind of small.
It's a 2-to-1 ratio.
Yeah. It's a potato. We'll have pictures of it, actually.
Okay.
They're not very good, but I just want to warn you right now.
Perfect.
So the aphelion, so it's the farthest away from the sun. It's 35.14 times the distance from the sun to the Earth.
Oof, that's far.
It's actually going to hit aphelion on December 9th of this year.
Hey, happy birthday.
Yeah. And perihelion's at about 60% of an AU. And that's coming on July 28th, 2061. So that's when it's coming back.
Okay. All right, I'll mark my calendar.
Yeah. We'll be alive to see it, assuming nothing bad happens. So the comet's period is about 74.7 years. So about 75 years. That's someone's lifetime. So that's why Halley's Comet is actually rather iconic, because it's a short period comet, but it also has great naked eye visibility. So you don't need binoculars to see it. You can see it at night. Just looking
awesome.
up at it. And that's when it comes back, we'll see it.
Okay.
Right? And since it's a short period comet, you can see it up to 2 times in your life. Right? Famously, Mark Twain was born when Halley's Comet visited it in, I think, like 1835, and then he died when it came back in 1910.
Oh, so he haunts it?
Yeah, it's a ghost comet, yeah. He actually was beamed back up to it. Wait, no, that's Hale-Bopp. It's a different comet.
It's a different one. Yeah.
Heaven's Gate. Not. Oh. So because you can.
Well, this one's just for Mark Twain, though.
Yeah, just for him. He's going back home.
Only him. It's the only one who could do it.
So because of this, it's an iconic comet. I think the earliest traces we have of it historically are from like 582 BC.
Oh, nice.
Yeah. Because, again, it comes back once or twice a lifetime. So it kind of becomes a thing.
Yeah.
So in 1986, though, we have this thing called space travel, which means we can go take pictures of it up close, right?
Oh, we can go visit it. We
Yeah,
don't have
visit
to be Mark Twain.
Yeah. We can go visit Mark Twain up on Halley's Comet.
Yeah.
So a series of missions were launched to Halley's Comet in 1985, because it's early 1986 when it shows up, called the Halley Armada.
Ooh.
So one of them's called Giotto. This is ESA's first interplanetary spacecraft. It's on my list of episodes that you should make a list for.
Okay.
Then we have the two Japanese probes, Suisei and Sagakaki. We talked about those when we talked about Haita and Hagoromo.
Okay.
And then, so the United States, we were going to have two missions specifically to look at it. One was called Spartans. That's another one of those shuttle payload bay experiments.
Okay.
That was on STS-51L.
Okay.
It was destroyed on that flight.
Dang it.
And then there was another mission called Astro 1 on STS-61E. That was going to come in March 1986. That was obviously canceled. But for us, in NASA in America, we have
the greatest country on Earth.
Obviously, America. Yeah, we were talking about this Soviet mission. We got to talk about how great America is, okay, comrade?
Yeah. Come on, we got freedom and Coca-Cola.
Yeah. The Soviets, you know what they got? Oppression and Pepsi.
Yeah. Exactly.
So we have
Here, just hang on a second. I gotta take a quick sip of my Mountain Dew.
Who owns that? Is that Coke or Pepsi?
That's Pepsi.
Oh, all right, good. You're a good comrade. You're drinking your Pepsi. Oh gosh. So for America, we have International Cometary Explorer, also known as ISEE-3. That's an episode that's coming up soon. We have Pioneer 7, which is still active at this time. Pioneer Venus Orbiter, right? That's our contribution as Americans to the Armada. Now, there's two other spacecraft that we're doing. This one, Vega 1 and Vega 2. These guys.
Ooh, okay.
Yeah,
they look very Soviet.
I know, right? Look at this. Yeah, this is Soviet. It's so interesting to see different spacecraft designs, and you can know this is American, this is Soviet.
They're very distinctive form languages, yeah.
Yeah, it's so interesting. So this is a mock-up of the Vega spacecraft, what we'll be talking about, and this is the Vega Lander. This is the actual lander.
Oh,
actual picture. Okay. I have actual pictures of the hardware for this mission.
So this is the ones that actually flew. So this is after they retrieved them, obviously.
Yeah, after the Soviets went and retrieved them.
Yeah, they walked over, back to Venus and picked them up.
One thing I forgot to mention, we'll talk about at the end. This is the last successful Soviet interplanetary mission and Russian interplanetary mission.
Oh.
In 1985.
Yeah.
So this is that. Yeah. So this right here fits in this. In there. That's what's carrying it. It's in there.
The big orange sphere.
Yeah. The ball. The orb. And then behind it, you can see the other part of the mission, an aerostat.
That is not orange. That's
a balloon.
It's white. Yeah.
That's a balloon. Yeah.
It's a balloon.
So this is our spacecraft. This is a mock-up of it. So one thing that isn't in this image is the heat shielding and like the insulation on top of all of it. Yeah, I know it's Soviet. It's got all the pipes and wiring everywhere, but
it'd be covered in insulation.
Yeah. There's a picture of it, actually, I have. Okay, so there's 3 parts to the spacecraft. Okay? So there's the main spacecraft bus. That's this guy minus the ball. Okay? This is going to support the entire mission. It's going to carry the lander and atmospheric probe on a flyby of Venus before heading out to rendezvous with Halley's Comet. So this trajectory actually does a flyby of Venus. It doesn't actually enter orbit or anything. It just drops it off.
So it just drops it off at its friend's place while it hits the bar.
Yeah, it doesn't even stop, right?
I'll slow down for you. You can get out.
Yeah, get out.
Tuck and roll.
Yeah. This over here, then, is the lander. So this component lands on the surface of Venus to study the atmosphere and exposed surface features, so the rocks of the planet. It's identical, pretty much, to the other 6 Venera landers. Now, for these landings, these spacecraft should last about an hour.
Oh, again, because of the heat.
92 atmospheres of pressure,
Mhm.
and 867 degrees Fahrenheit.
Okay.
It's pretty hot
Yeah,
and toasty in there.
Yeah, that's a pressure cooker.
Yeah. This is a night landing, so there's going to be no pictures of the surface.
Oh, okay.
Yeah. And then on this...
What, you didn't bring a flashlight?
don't think it would have survived.
Yeah, probably.
So the other thing, the unique part of this mission are the 2 balloons, one on each spacecraft. These are atmospheric...
party balloons.
What?
Party balloons.
Oh, yeah. Good party here, comrade.
Yeah.
Again,
we landed on the Venus.
And that's the actual balloon. That's an actual photo of them testing it.
Okay.
So these are meant to monitor the middle atmosphere of Venus, which is 53 to 54 kilometers in altitude, or 32.9 to 33.5 miles above the surface.
It's a cruising altitude.
A bit higher than that. I actually have a reference to how high that is later.
Okay.
Where there's a lot of activity in the atmosphere. That's what they want to study.
Okay.
These are the first and only balloons to ever be used on a celestial body that's not Earth. Only
cool.
time.
Because I know that, I know not balloons, but on Mars, they recently put on that helicopter.
Yeah.
Yeah.
That's the first U.S. thing that does that.
Yeah.
I know I know there've been some studies for balloons on Mars.
Okay. Doesn't have much of an atmosphere.
Yeah.
So
The place is kind of dead. No atmosphere. Got that joke out of our systems. Okay. No comments. Just gonna stare at me. Okay. So here's what's on the Vega flyby Comet Intercept module, which that's a cool name. The Comet Intercept module.
yeah,
So this is what it looks like. There's some diagrams of it. Now,
it's what we just saw, basically,
yeah,
right?
it's got stuff on it. Now, Vega comes from the Soviet-Russian way of pronouncing things. So Venera is Venus, and then Galley is the way of doing Halley's Comet. So it's the GA, right? VEGA.
Okay.
That's where it comes from.
Got it. Okay.
So I couldn't find an accurate number for how much this thing weighed at liftoff. I couldn't. Every source used a different number.
Awesome.
This is the fun part of doing Soviet space missions.
Well, it's not like public domain like with NASA?
Of course it's a public domain, comrade. The Soviet Union
These are
is
people's
space program. Yeah, run by the military. So the number it is. The Soviet space program never disentangled itself from the military. So it's all
cool.
still technically like part of the missile. It's interesting how they operated it. So the gross liftoff weight is somewhere around 5 metric tons. So it's about 4,840 kilograms. So that's about 10.6 thousand pounds. So it's kind of fat and heavy. One of the reasons for this is because the avionics and electronics are pressurized.
Okay.
Which means it's in a pressure vessel, whereas ours are actually exposed to vacuum.
Okay.
It's a unique problem set. For exposing it to vacuum means it weighs less, but you need better thermal management of our electronics.
Got it. Right.
Whereas the Soviet way of doing things, which is pressurized, you have to build and maintain a pressure vessel and have built interfaces for that. So it's the hard way of doing things. So this actually has an engine on it in the bottom down here.
Under all that stuff.
Yeah. I can't remember which part's the propellant tank and which part's the electronics bay. Because a part of me says that this is the propellant tank. Or
No, you just put the electronics into his propellant. He'll be fine.
Yeah, this is where all the Pepsi's stored for maneuvering. So it actually has a maneuvering engine, a KTDU 425A engine, specific impulse of 315 seconds, runs an NTO UDMH, which that's to be a given. The thrust is 9.86 kilonewtons, so it's about 2,200 pounds thrust. Pretty decent.
Okay.
Again, for something that weighs 10,000 pounds,
It's not great.
It's got 2 solar arrays. Well, in space, it's more about specific impulse. I mean, you don't want it to take 10 hours to do a burn, but,
Right. Yeah.
it's a mix and match of things. It's got 2 solar arrays, as you can see.
Yeah.
Now, this one, the modification from the basic Venera mission bus is it's got a micrometeorite dust shield.
Oh, right, because it can be flying through the comet.
So there's 3 kinds of experiments on this spacecraft. Well, it is tanks and thruster. I just noticed that. There's a
Yeah. Yeah.
I can't read.
It's a diagram.
Yeah.
In English.
I did find one in Russian.
But that was helpful.
That would have been really funny if I put that one in. It's like, there's stuff here.
And as you can clearly read.
And it's, KGB, open up! You're like the FBI one, you know?
Yeah.
Actually,
KGB, open up.
yeah. So there's 3 kinds of experiments on this: optical, dust, and then the analysis of gas, plasma, and fields.
Interesting.
Yes. So the optical systems, we have a television system, a 3-channel spectrometer, and then an infrared spectrometer. It's got a TV camera on there.
Nice.
And then
broadcast the game.
Yeah. For the dust counters, there's a lot of them. There's 4. It's 5. Puma, dust mass spectrometer. SP1 and 2, dust particle counters. And then DUCMA and Photon are dust particle detectors. Just to be clear the difference between them, it's the mass of the dust that it's counting. It's different between the experiments.
So it's like one's bigger, the other's smaller dust. So it's different flavors of dust.
Yeah, obviously.
And it's got different taste testing equipment for that.
Yeah.
Okay.
And then for the gas, plasma, and fields experiments, there's ING, which is the neutral gas mass spectrometer. You got Plasma G, top G, cometary plasma spectrometer. Tunda, that's the East German contribution to this mission. Because, by the way, this is a Soviet international one. So it's Czechoslovakia, Hungary, East Germany, Poland, I think, and then France.
France.
Yeah. It's the balloons. So they got Tunda M, energetic particle analyzer. Misha, the magnetometer. That's actually what this is. It's the big one here. You got APVN and APVV, which are the wave and plasma analyzers. So you kind of see where everything is. Yeah. So right here's the TV system. That's the cameras. You got dust counters. So many dust counters.
Gotta count all that dust. There's a lot of dust to count.
Yeah. You think all the German experiments will be the dust counters?
Yeah, you'd assume, but
so here's the engine. That's it.
That's well.
Yeah. Huh. Look at that. All that plumbing. Yeah, I think it's pump fed too, which is weird.
Yeah.
Again, very Soviet.
Yeah.
We just put
I like how
pressure
there's just this giant pump for this little engine.
Oh yeah. It's scalability of small engines with pump cycles is actually not that good. That's why Rocket Lab is using electric pumps. There's no weight savings. It's just they scale better at that size.
Makes sense.
So this is a diagram of our camera system. So this thing is that down there.
Right, the thing hanging off the side.
Yeah, which doesn't deploy until they get to nearby Halley's Comet, which I think is interesting. So there's the TV camera. That's this. They got the 3-channel spectrometer here, and they got the infrared spectrometer. That's what this is, or a harpoon gun, I guess.
That's what it looks like.
Yeah, and that's the actual camera. It's right there.
Okay.
So we have our lander. Okay. So again, I don't know how much it weighs. About 2 tons.
Okay.
It's about 4,400 pounds. The sphere it's in is 2.4 meters in diameter, so 7.874 feet.
It's about 8 feet.
Yeah. So the lander's the same design that was used on Venus during previous landings, so it's basically identical design. So aside from basic temperature and pressure sensors, there are 11 experiments on the lander. The balloon is mounted up top here, and it will be deployed at roughly 61 kilometers, or 37.9 miles.
Got it.
The images are coming up for that. So it's kind of stored up top here. And this is actually an antenna. It's a helical antenna, which I think is interesting.
Yeah, I always wonder about that, because it looks like a screw, you know?
It's a helical antenna. Yeah.
I always thought it had to unscrew it, like
a light bulb, right? That's what you mount it to the main spacecraft bus. Come on, guys, we got to deploy it. Let's unscrew it first. Give me a second.
Yeah, how many cosmonauts does it take to unscrew the Vega Lander?
I don't know. So
none. He deploys by itself.
Yeah. The wrong way.
Yeah.
So here are the experiments. ISAVS, which is a UV absorption spectrometer. ISAVA, an optical aerosol analyzer, and nephelometer. That just determines how bright things are. Or no, that's the aerosol concentration. It's like a dust thing.
Oh, okay.
It's air quality kind of thing.
Got it. Figure out, how breathable is Venus's atmosphere?
It's 98% carbon dioxide. You can breathe it once.
Oh, okay.
Yeah, take a deep breath.
Good enough for me.
Yeah, the LSA, which I don't know where that is on here. It doesn't point where that is. The aerosol particle size counter. Malachit M, the aerosol mass spectrometer. Sigma 3 aerosol gas chromatograph. So that's this. Then you have IFP, the aerosol X-ray fluorescence spectrometer. Then you have VM4, a hygrometer. So that measures like the water content, because there actually is water in the atmosphere of Venus.
Oh, nice.
The BDRP AM25, a soil X-ray fluorescence spectrometer, which
So looking at how many fluorescent light bulbs are in the
yeah,
in the ground.
yeah, it's for this, right? It's got to screw it in, right?
Oh, right, yeah.
There
You
we go.
screw it in and then it turns on.
The GS15STS, I think that's a specific Cyrillic letter. I think that's what that is. V, the gamma ray spectrometer, which, wait, I just saw that.
Looking at gamma rays.
Yeah, there's radioactive. I actually have diagrams of the individual experiments coming up, so we'll talk about that. They have
Okay.
Prop V, the penetrometer soil ohm meter. So it's going to penetrate the soil and see if it's electrical or not.
Flow the current.
So it's a little outlet. Just, come on.
Yeah.
They have a stabilized oscillator Doppler radio, so that's for when it's landing. Yeah, so this
Okay.
is what the spacecraft looks like. So you got soil sampler, the instrumentation bay. Most of it's in the pressure vessel, which in this case I understand putting in a pressure vessel, right?
Yeah, that actually makes sense.
Yeah. So here's the
The
actual.
whole planet's a pressure
Oh
cooker.
God, it is. What a nightmare. So this is the ISAVS. So the Venusian atmosphere is actually far more interesting and dynamic outside the visual spectrum. So if you ever see that picture of Venus where it's blue with white clouds that are like banded,
Yeah.
yeah, so that's it in UV.
Oh,
That's
okay.
what it's way more dynamic and interesting. Oh, and the one fun fact about the Venusian atmosphere is that it's called super rotating.
What does that mean?
It means that it's spinning faster than the planet is.
Well, I mean, that makes
Right,
sense.
because Earth's atmosphere basically goes with the rest of the planet, right? It travels around the Earth in 24 hours, roughly. Yeah, you got things like hurricanes and wind, but pretty much the whole atmosphere is rotating with the planet. Not on Venus.
It's just doing its own thing.
It just does its own thing. It's super rotating.
It's like, wow, this place sucks. It rotates
Yeah.
not even twice a year. Like, we're gonna do our own thing.
Right, because it's baking one side of the planet, right? The sun.
Yeah.
Which also does remind me, I think we discovered jet streams on Venus before we discovered them on Earth.
That is weird.
We also discovered a polar vortex on Venus.
Do we discover that before discovering it on Earth?
Yes.
Okay.
We actually
So
found-
we did meteorology. We understood meteorology better on Venus before we did it on Earth.
Well, with Venus, you have this massive atmosphere that's just doing weird stuff that you can see a lot
Yeah.
better than on Earth. So that's why.
Makes sense. Okay.
So at the time, there's an unknown chemical performing a lot of UV absorption, and they're going to try to figure this out. So they're going to analyze
Okay.
the spectrum between 230 and 400 nanometers, which is in the UV spectrum. So it's going to actually take in samples of the atmosphere and analyze them.
Because isn't 400 nanometers? That's like right at the edge of like violet light.
Yeah.
Right.
So then this is Malachite. And do you like how this looks? This is a black and white image made to look like it. Does that look good?
Yeah, it looks good to me. Does it look good to you,
Of course it does.
dear viewer, listener? Leave in the comments section below what you think.
Yeah. So Venera 9's experiment, which is basically the same version of this, that the Venusian clouds are more than just sulfuric acid droplets. Pioneer Venus's atmospheric probe and Venera 12's found chlorine and iron in the atmosphere. So they're trying to figure out the
Ooh.
atmospheric chemistry of what's going on.
Yeah, what's it made of?
So what this is going to do is collect cloud samples as it's going down, and then perform mass spectrometry on the samples to determine their composition.
Okay, figure out what's all going on up there.
Yeah. So this is Sigma 3, which looks scary to me. I don't know why.
Why does it look
I
scary
don't
to you?
know.
Is it because of all of the stuff on it?
Yeah.
All the sharp angles and sharp edges?
Yeah.
The very Soviet design?
Yeah. So this has been designed to measure the amount of sulfuric acid in the atmosphere.
Okay.
So then this is our soil end drill motor. This is the actual thing. So it's going to analyze the
Ooh.
crust of Venus. And this is
Yeah.
actually an engineering marvel because it's designed to operate after it heats up to 500 centigrade.
Oh.
Yeah. It doesn't work at Earth temperatures like this.
So they built it specifically for Venus.
Yeah. Again, Soviet technology is, for the most part, subpar compared to what we have in America, except in a few areas where it's just, how did you make this? Right?
Suddenly they defy the odds. It's just
Yeah.
like, what?
How did you do this? Space is one of those areas where they just really did. Oh, they did pretty well in.
Yeah, pretty well. It's a wide array, a wide contrast of.
Soviet Union's a land of contrasts.
Yeah.
So what this is going to do is it's going to take a sample from the soil and then transfer it through a series of little airlocks and put it into the X-ray fluorescent spectrometer.
Okay.
So you can see what it is and what it's made of.
Got it.
This is the gamma ray spectrometer and a pen. You can see it's
cool.
a pen. That didn't go to Venus, I
There's
hope.
a pen.
I hope. Yeah. So this is a scintillation counter to measure the energy spectrum of gamma rays from naturally occurring radioactive elements. Potassium-40, uranium-238, and thorium-232.
Okay.
Potassium-40 is what makes bananas radioactive.
So if I eat enough bananas, I'll die of radiation?
Someone did the math. You'd probably more die of just food poisoning at that point.
Oh.
Eating so
Dang.
many bananas. And these over here are the temperature and pressure sensors. I couldn't find any pictures of the other equipment, unfortunately.
Oh.
Yeah.
Dang. Well, okay.
It's supposed to take the temperatures and the pressures on the surface, and as it goes down.
Got it.
And the star of the show, the balloons.
Balloons! Yeah!
And these are French, so they're snooty.
It would be the French. They were the first ones to do the
Yeah.
balloons.
Yeah, the Montgolfier brothers. They dug them up specifically to make these. I'm like, what are you doing?
I need you to build a balloon. Put it on another planet.
Yeah. So these weigh about 50 pounds. The balloon's diameter is about 11.16 feet, so it's pretty big.
Pretty
So
decent.
the first time this French actually thought about doing this was in 1967.
Oh, wow.
Yeah, to study the atmosphere of Venus, right? Because how else you can explore the atmosphere than with balloons? Because you put a lander and it's only going to do it for about half an hour, and then it's going to hit the surface and then die. But if you got a balloon, you can do more.
Right.
So the original plan was these to be on Venera's 11 and 12, but those were delayed due to strains in the relationship between France and the Soviet Union. Also, apparently France had a whole bunch of strikes.
What are they not striking?
I know. That just seems like France being France.
Yeah, that's French culture.
Yeah.
Yeah.
And these are the first and only balloons on another planet to date. Obviously, you might see some more coming up in the future.
Yeah.
Have there been other planets? I don't think so. We'll talk about it at the end.
Okay.
So there are 5 experiments on the balloons. They're pretty simple. A temperature sensor, an anemometer.
Figure out how hot it is.
Yeah. An anemometer, which measures wind speed. A photometer, that measures the brightness.
Got it.
A pressure sensor.
How pressure is it?
Yep. And then a nephelometer, which measures aerosol light scattering. That's what that is.
Oh, okay.
And
So
then,
it's just like how diffuse the light gets.
yeah, because right, you got different atmospheric conditions. What's Venus like? Because Earth, not much. Venus,
Yeah.
a lot.
Yeah.
And the battery lifetime, it's a lithium-ion battery, I think. Yeah. Which is 46 to 52 hours, roughly. That's the lifespan.
It's about 2 days.
Yeah. So this is what it looks like. Oh, wow, that's a lot of pixels. So it's got a semi-directional antenna. That's what the cone is up front. Little spiral cone. It's not candy. It's an antenna.
Oh.
It's got the radio transmitter electronics. It's got the sensors here, the anemometer. Yeah, it's a little balloon package on Venus.
Yeah, it's basically just on a stick.
Yeah, which, I mean, that's kind of what we do here on Earth, except our balloons are bigger. Notice the picture of the Chinese balloon a few months ago or a year ago that scared everybody? That's way more advanced than any of this.
Yeah.
We built something like that too, just to be clear.
Oh, yeah.
So here's the actual spacecraft again. This is what it looks like. So these things here, these guys, are for steering, for stability as it comes through the atmosphere.
Oh, okay.
Yeah, so this is pretty much a giant drag shield.
Oh, okay. So that's what that is.
Yeah.
All right.
And here's the atmospheric. I think this is the soil sampler here.
Okay.
I can't remember where everything is now.
That's the gas stuff.
Yeah, the gas
for the
chromatograph.
UV. Yeah.
Yeah. And these are just shock absorbers for the landing.
Oh, okay. So just a nice soft landing on the pressure cooker planet.
And this is the spacecraft being integrated. And again, another guy with a beard and glasses that looks kind of like me.
He's got a much fuller beard
Yeah, he
than
does.
you, I'd say.
Yeah, my beard sucks. Thanks for reminding me. So this is what the spacecraft looks like with all the insulation on top of it.
Yeah, that's why. Okay, so it looks baggy.
Yeah.
That's
Yeah.
the insulation. Okay.
So this is the launch. This is launch of Vega 1 on a Proton.
Ooh. Okay.
Isn't that a cool rocket?
Yeah, it looks cool.
Yeah. This is the one that famously had the accelerometers in upside down that one time a few years ago.
Oops.
Yeah. Which is funny because those accelerometers are designed to be put in the correct way. How did you screw that up? I don't know.
It has to have one side says up, the other side says down. You have to have a big arrow. You
That's
know,
true.
like with cardboard boxes, it says this side up. You know, it's got
true.
a big arrow pointing up. Yeah, that's what you need.
Yeah. So this
Visual cues.
Yeah. So this is the launch of Vega 1. I couldn't find a picture of the launch of Vega 2. It's in the Soviet Union. You know, who knows? Don't breathe these clouds. This is somewhat dust. It's also nitric oxides, which don't like your lungs.
Oh, okay. So I should breathe it in.
I mean, for the rest
Wait,
of your life.
is it nicer or worse than Venus?
Nicer.
Nicer. Okay,
Well,
so
it depends.
breathing this would be
How
preferable
long do you want
to
to suffer? Venus,
Yeah.
pretty quick. Right? You'll take a breath, it's kind of over. This, you'll suffer for a bit.
Yeah, this one, yeah, you die instantly on Venus, where this one you prolong along a little bit,
Yeah.
and then die. Okay.
So this is the launch. So here's the trajectories that we're going to take. So Vega 1 launches on December 15th, 1984. Vega 2 launches 6 days later on December 21st, 1984.
Merry Christmas.
On Protons. So the milestones for Vega 1. So on June 9th, 1985, that's when they separate the lander to dump it on Venus. And
Okay.
then June 11th, 1985 is when it lands on Venus.
Got it. Okay.
And then from March 4th through 7th, 1986, so almost 6 months later, that's when it flies by Halley's Comet, so you can see it here in the trajectory.
Okay.
Yeah.
Yeah.
And then for Vega 2, it's just offset by a few days, right? June 13th, 1985 is when they separate the lander. June 15th is when they land. And then March 7th through 12th is when they have the encounter with Halley's Comet.
Okay. So they're only off by like 4 days from each other.
Roughly. Which, that kind of makes sense, right? Orbital mechanics working out the way they do.
Yeah. Yeah.
So now, this is the landing sequence, okay?
Okay.
So,
Okay.
at 125 kilometers, that's 78 miles, that's
Okay.
when the Vega Lander hits the atmosphere at 11 kilometers a second.
Okay, that's pretty fast.
Which is about what the Apollos hit the atmosphere at.
Okay.
But you gotta remember, you ever try to land on Eve in Kerbal Space Program?
Yeah, that's hard.
That's tough. Yeah,
Yeah.
this is the same problem.
Okay.
So at 64 kilometers, so 40 miles up, that's when the landing cap opens.
Okay.
15 seconds later, about a kilometer down, the parachute's deployed.
Okay, so, all right.
Then 40 seconds after that, that's when they release the balloon. At about 61
Okay, so-
kilometers.
Okay.
Yeah, so you can see it's dumped.
Right. Get out of here, balloons.
It's out. Go party somewhere else. Without me.
Yeah.
So then the second parachute opens at 55 kilometers. So you can see that. It's not in this diagram. So then at 54 kilometers, the balloon is inflated about 100 seconds after it's dumped from the lander.
Okay.
So they drop it on a parachute, then it inflates with helium and rises up. So the
Got it.
balloon ballast releases, and it drifts back up to the altitude it's supposed to. So then at 47 kilometers, they just dump the parachutes and land.
Oh.
The atmosphere
So
is
just-
so thick that they don't need parachutes.
Oh.
Again, that's what the dish on top is for. That's the drag surface for landing.
That's the drag. It's so thick. All you need is a drag
Yeah,
surface.
it's going slow enough. We'll drop it.
Dang.
And on Vega 1, at about 20 kilometers up, something happens where it suffers a shock.
Oh.
We don't know what it is. The theory is that as it was collecting atmospheric samples, it just jettisoned them accidentally.
Oh. I thought I hit a bird. Or
Yeah,
something.
hit a bird on the way down. Yeah.
Yeah.
How'd this happen, guys?
We discovered alien life and then proceeded to kill
Yeah,
it.
the only life on Venus was hit by Vega 1.
Yeah.
Of all the things that could have happened on this giant planet, there.
Yeah.
So what happened?
Very unlucky.
Yeah. How Soviet. So what the problem is, this shock then tells the lander, "Oh, I've landed." So it deploys all but one of the experiments.
Oh no.
So they don't work when it hits the surface. Because again, it's Venus. They're not going to last long.
Yeah.
So the Vega 1 lander, I don't actually have an official number for how long it lasts. It's about 20 minutes.
Okay.
And Vega 2's lander lasts about 56 minutes. So it's about on average, right? It's about an hour, which that was probably the longest hour. If you were on Venus experiencing that heat and pressure, that would be the longest hour.
Yeah.
Oh, it'd just be miserable.
Man. Hey, yeah, you've walked outside in the Arizona heat.
Oh, yeah. Or
Yeah.
Alabama when it's hot and humid. Oh, it's miserable.
Gosh. Yeah. No,
Now
that's
it's
pretty bad.
way worse.
Just like Vietnam, except way worse.
Yeah. So the balloons operate on average about 53.6 kilometers or 33.3 miles. Now, remember the Red Bull jump about 10 years ago?
Yeah, like it set the record for like the highest jump.
It's the second highest. A guy like the week later from Apple did the same thing from like 10 feet higher.
Oh, okay.
That's at 39 kilometers or 24 miles.
Oh, so this is much higher than that.
Way higher. Yeah. And for Vega 1 and 2, they last 47 hours. There's actually a network of ground tracking stations on Earth that track this, including one in North Liberty, Iowa, which I thought was interesting.
Yeah.
North Liberty, Iowa is in like Cedar Rapids, for reference.
Yeah, okay. Still don't know what that is.
We drove through it when we were coming down to visit me.
Okay.
Yeah. So Vega 1's balloon travels 11,600 kilometers, or 7,200 miles.
So that's a good distance.
Oh yeah, it's going about like 260 kilometers an hour.
Which is like what? How fast
150 miles an hour.
So it's just booking it around the planet.
Oh yeah, they travel I think 30% the circumference of Venus in 2 days. So Vega 2 does 11,100 kilometers, which is like 6,900 miles over the period. Again, now here's the fun fact. That's just how long they lasted. The transmitters. They probably lasted in the atmosphere a bit longer.
Yeah, they probably went around Venus in like 3 days.
Yeah. So they actually travel from, because again, they land on pretty much the antisolar point, so the spot that's the exact opposite where the sun's facing.
Okay, so the dark side of Venus.
Yeah, the very far dark side. They cross into the day side.
Oh.
Yeah. So then for the Vega spacecraft, they do a flyby of Venus and then head on the way to Halley's Comet.
Okay.
So this is the landing sites. So you can see, so this is where all the Veneras landed, right?
Ooh.
So this is,
okay.
Yeah. So
it's around the equator.
Yeah, and again, when we start talking about these kinds of missions, I know in Kerbal Space Program it's pretty easy to enter polar orbits. In real life, it's way harder. That's why all the Apollo missions landed near the equator of the moon. Because that's what you could hit.
It's easier.
Yeah.
Yeah.
So you can see, right, all the Veneras in Vega over here.
Yeah.
So this is
the other side.
So this is Aphrodite Terra. This is what the continent
Okay.
is here, which you can't read on this. Yeah, Aphrodite Terra. It's the big continent. I think this is called the Medusa Plain, where they landed.
Okay.
Again, this is the exact opposite side of the planet than where everybody else did.
Right.
So let's go to Halley's Comet.
Okay.
So the Comet flybys are from March 4th through 12th, 1986. Obviously, the space shuttle could not do any of those missions to observe this because...
Reasons.
Yep. So for Vega 1, the relative velocity at the counter was 77.7 kilometers a second.
Jeez.
For reference, Earth orbits the Sun at about, 35 kilometers a second?
About 30, yeah.
Yeah. So it's booking it.
It's going fast.
Right? The closest approach is nearly 8,900 kilometers, so it's about 5,500 miles.
Yeah, but at those speeds, that'd
Oh,
be
yeah.
pretty scary.
Oh, yeah, that's pretty scary. So it takes roughly 500 images of the nucleus. This is from Vega 2, I think.
Okay.
Because of the dust, which pulverizes it, they lose about 40% of the power.
Oh.
Yeah.
It's a lot of dust.
So-
That's why you want to count it so much.
Yeah. I can't really dust.
What is there for?
So for Vega 2, that encounters Halley's Comet about 80 kilometers a second. So again, really fast.
Yeah.
This gets a bit closer at 8,000 kilometers, so about 4,990 miles. This takes about 700 images of the nucleus, and then the solar rays on this one lose 80% of their power.
Jeez.
because they're just pulverized by dust.
Man.
And for a fun fact, the Soviets said that only about 36 images from these were actually good. This is one of them.
Oh.
Yeah. Not that very good images.
Yeah, but hey, I mean, that's like, what, 20%? Now, 20%, like 5% success rate?
Yeah. So there were plans for follow-ons for the missions. Vega 2 was going to do a 6 million kilometer flyby of 2101 Adonis. That didn't happen. So the problem was they had a lot of propellant left over for maneuvering, and the spacecraft were still doing pretty fine. They just did mission planning to see what could we do a flyby of next, right? Because you don't want to waste the spacecraft. Nothing. There was nothing they could do. Nothing interesting. So they did fly through the orbits of 3 comets, 72P Denning Fujikawa, Biela's comet, and then 289P Bland Payne to measure dust as they flew through the orbits of them, right? More dust counting. I couldn't find any data on this. I don't know if the data exists or it's some, on some cassette tape in a Soviet style in some guy's, closet. I don't know.
My cousin has it.
Yeah, he traded it for Pepsi. So for the end of the mission for both these spacecraft is in early 1987. Vega 1 loses all of its propellant on January 30th, 1987. And then Vega 2, they just lost contact with it on March 24th, 1987.
Oh, okay.
Yeah.
Again, communication.
Yeah, another communication problem. Electronics failed again.
I mean, it did lose 80% of its power, counting all the dust.
Oh, yeah.
It was exhausting.
So here's probably the best image of Halley's Comet that they got from Vega 2.
That's very bean-shaped.
It looks like a potato. They all look like this.
Yeah.
This is what the average image looks like, though. This one's cleaned up. This is what they all look like.
It looks like a spotlight.
Yeah. It's like all that. It's all dust from the sun, right? There's dust and there's sun. There's jets. I actually found how they kind of analyzed it, how they kind of filtered through of it. It's kind of interesting. I think it's in one. I have like 24 references for this one. I found a lot of papers on it that talk about how they cleaned up the images. But you can see here it is. There's dust jets coming off because it's a comet, right?
Yeah, that's what it's doing.
So let's talk about some results.
Okay.
So these are from the landers. Now this is radar images from Magellan.
Okay.
This is from our last mission to Venus from the 90s.
It's from our American freedom imagery.
Sure. So this is the Vega 1 landing site. And don't let this fool you, make it look like they're pretty close. So that's 0 degrees, 5, 10. So these are pretty far away, right?
Oh, okay. That's latitude.
Yeah. So this is the equator of Venus. So you can see here kind of in terms of volcanisms, you got Sapis Mons over here. You got a ridge belt, wrinkle ridges. So, get some face cream. That'll fix that right up. You got some volcanic flows, small shield volcanoes, more flows. Sith corona.
As opposed to Jedi corona.
Yeah, that's on the other side. So this is what the landing sites look like radar mapped. I actually found a paper on this. It was really interesting. All the different landing sites.
Dang.
So
yeah, jeez.
So obviously most of the data we get is from Vega 2 because Vega 1 failed for the most part.
Yeah, it hit a bird on the way down.
So the surface conditions where Vega landed, 467 centigrade, which is about 872.6 Fahrenheit at 94 atmosphere.
Jeez.
It's just, again, it's going to pulverize this thing.
It's toasty.
Vega 2, it's a bit chillier, okay? Put on your winter coat. 461 centigrade, 861.8 Fahrenheit, 91 atmospheres. So it's not that bad.
Yeah.
But with 240 kilometers per hour winds.
So the wind is just bucketing.
Oh, yeah. I've actually seen a mission proposal for a Venus rover that's just a land sail vehicle.
You have the wind.
Kind of like in, what was it, Sahara? When they got that plane wreckage to like that.
Yeah, imagine that, but like 10 times faster.
And melting.
Yeah.
So the first one we're to look at here for results is the radioactive material compositions by weight percent. So
okay.
For these,
how much radioactive material there is.
It's consistent with all the other landers. You want me to go into the specific numbers?
I mean, we have a chart there.
I did.
Right?
I made that chart, by the way. Does it look nice?
Yeah, it looks really good. Thank you.
Yeah. So potassium, it's about 0.45% plus or minus 0.22. That's about normal what you get like on Earth. So again, it's a very, very close planets. Vega
Right.
2 kind of correlates that. It matches the rest of the Venera landers. For uranium, times 10 to the negative fourth, just remember that. It's just 0.64, 0.68. For thorium, it's about 1.5 times 10 to the negative fourth. Plus or minus 1.2, so that's a bit of a range there on those. So the thorium, it's a bit harder to detect that one, I guess.
Yeah.
So
the thorium might exist, it might not exist.
Yeah.
That's the error margin we have.
it might be there. So the surface rock oxide compositions by weight percentage. It's not in order of, not any particular order, as I discovered when I was typing this out. So the most common one is silicon oxides, which is consistent with what Earth is. Same thing with Earth.
So it was mostly made of rocks.
Yeah. Look at this. This planet's made of rock. Wow. Right. You got some magnesium oxide, a lot of aluminum oxides, silicon oxides, sulfur oxides, potassium oxides, calcium oxides, titanium oxides, magnesium oxides.
How close is this to Earth?
Well, we're to talk about that. It's the next paragraph.
Oh,
So the
okay.
surface composition shows that this is olivine gabbro norite. On the north, now this is this is here. This is the northern slope of Aphrodite Terra here, right? This is the Medusa Plain, MP,
Okay.
and then this is Aphrodite Terra here.
Okay, so that's the high land versus the low
lowlands.
plain.
So if we were to flood Venus, these would be underwater.
Got it. Okay.
Right. So surface composition is olivine gabbro norite, which is very similar to what the lunar rocks were like in the lunar highlands.
Oh, really?
And olivine is, I think, the most abundant mineral in Earth's crust.
Okay.
Which makes sense.
I mean, it is a really cool name,
Yeah.
like olivine gabbro norite.
Yeah.
That's awesome.
Yeah. So Earth's crust is made of like olivines. So there's different types of olivines. I'm not a geologist. I'm just gonna stick that. I thought about geology because I was really inspired by the core. I actually considered switching over to geology when I was in college, but then I remembered one important thing. I suck at chemistry. What does this look like to you?
That looks like
It looks
chemistry.
like chemistry. Rocks are
Yeah.
pretty cool. Understanding how they work, that's pretty neat. I don't do that.
Yeah. Not trying to make the crystal.
Yeah.
You know.
I make different kinds of crystal, okay? So the surface composition of Venus for all of the Venera landing sites, including Vega, are volcanic basalts of some kind. Right?
Really? On a volcanic
I know,
planet?
right? Isn't that weird?
Wow.
Shock of all shocks. What are these?
Yeah.
Volcanoes.
Wow.
Volcanoes. Actually, I just remember reading this a few months ago. Someone confirmed there's active volcanism on Venus by looking at old Magellan radar data.
Really? Active volcanoes
Yeah.
on the volcano planet?
Well, that's the thing. We thought it was dormant volcanism. There's just it's like volcanoes that weren't active.
Oh.
Yeah.
So just a bunch of dead volcanoes. But
Yeah.
there's actually
there
active
might actually be
volcanoes
active volcanism on Venus.
on the volcano planet.
Yes.
Wow. That's shocking.
So, for example, so I made a list of here some of the. So Venera 14 landed in alkaline basalt, so it's got a lot of alkalines.
Okay.
Whereas Venera 9 and 10 were young shield volcano geologies.
Okay.
Which, again, you like rocks? This is pretty interesting.
Yeah.
It is, because again, that's what
Yeah.
Venus looks like.
Very rocky.
Except for the atmospheric composition. So this chart here shows the composition of sulfur oxides, and so you can notice here this is like the parts per million of it.
Mm-hmm.
So you'll notice that somewhere around between, you can see right here, there's just something going on at about 47 kilometers in the atmosphere, right? Because these are from both Vega landers, right? Or the different counters. You can see there's kind of a chart. There's a lot more than boom. Something happens at around 47 kilometers.
Huh. What happens there?
We don't know. We've only
Something.
We've only been there twice.
Yeah.
So what was I saying? So 3 layers to the atmosphere. This is the middle one. Also, so this chart here is the chlorine, sulfur, and phosphorus count. I put it on its side for 60 to 47 kilometers, right? So from here to here, which is where this thing gets interesting. So you'll notice there's a lot of phosphorus right around here. So the idea is that there's sulfuric acid made in the upper clouds with photochemistry, right? The sun's beating down, and it's causing chemistry to happen.
Okay.
Like how right? When you look at paper and it fades over time, that's like photochemistry.
Okay.
Then it decomposes in the lower clouds, which in this case lowers, like 50 kilometers.
Yeah.
So it decomposes in the lower clouds, and it forms phosphoric acid. That's why we see a lot of phosphorus down here at around 50 kilometers.
Okay.
And this is why we want to count how much water vapor is in the atmosphere, because we want to see, because the water acts as a medium for a lot of these chemical reactions.
Okay.
Yeah, so this is the chemical composition of the atmosphere. I think it's pretty neat.
Yeah, that's pretty interesting.
Yeah. So this is the spectroscopy from Vega 1. You can tell because right here, about 20 kilometers, there's a shock.
It hits the bird. Yeah.
Yeah, that's the bird strike. So this is a different wavelengths, you can see, right? And then fiducial bar? I don't know what that means.
It's a line.
Yeah, it's just, I don't know. I didn't even see it on here. I don't know. So you can see, again, there's something happening in the atmosphere, 47-ish kilometers. That's just something weird's going on there for chemistry.
Yeah.
And then this is the optical thickness. This is how thick the atmosphere is, right? How far ahead can you see, right?
Okay.
So this is 0, which means you can look right through it. And then 10, of course, is you can't see. So again, you'll see, hey, you can see through all of it. Now you can't.
Right.
And obviously, there's the shock from whatever happened.
The bird strike.
And again, 47 kilometers, something's going on.
Yeah.
That's pretty
it
neat.
looks like it kind of looks like it peaks right about there, where it goes from like basically nothing to, because it's an logarithmic scale, right? So you can see it about there. It goes from like 0 to 1 up at 47 kilometers, then it goes up from like 1 to 5.
Yeah.
And then it just kind of stays there until the bird strike, and then it peaks up again at the at the basement.
So something is there's some like aerosols up there that's doing this. Yeah. And I was reading about like the composition of it. So one of the things they discovered was it's a different like clumping of the dust particles and the aerosols. It's not a new chemical. It's just different clumping of. It's how the aerosol dust particles clump together is different.
So some weird chemistry happens at 47 kilometers for some reason.
Something is happening there. So
okay.
So these are the balloon results. So what we have, this is Vega 1. So this is 1. This is 2.
Okay.
So these first two charts are deceiving you. This is higher. This is higher. So what you see here.
Oh, so it's upside down.
Yeah. So this is the altitudes for 51 to 53 kilometers. So the atmospheric pressure here at 53, where it was roughly staying, is 600 millibars, which is about 60% of an atmosphere.
Okay.
So it's sitting somewhere around 9 psi.
Okay.
Again, for reference, this is way higher than the Felix Baumgartner jump.
Right. Where he had to wear an oxygen.
He had to wear a spacesuit.
Yeah.
So you can kind of see how it varies. And then temperature-wise, so it's about 315 centigrade or Kelvin, which is about 100 degrees Fahrenheit.
Okay.
So it's not that bad. It's only an oven.
It's only an oven,
yeah.
Right? It's not a pressure oven. It's just an oven at that point.
Yeah. So this is gust velocity up and down. So it experienced a bunch of gusts. Oh, and somewhere around, so about here is where it crossed over into the day side.
Okay.
Right. So you can sort of see, especially in the brightness of all things, it picks up right around there. And then cloud backscatter, so that's how the light reflects off clouds. You can see this with that. And then the same applies to Vega 2. Right?
Everything goes wonky the second you flip over to the day side.
Yeah. Well, again, the sun's influencing things.
Yeah.
So for
you can see the if you go back, you can see the temperature spike up.
Yep.
With and the pressure as well.
Yeah, because it's the hot side.
And the gusts too.
Yeah. Well, again, the sun's influencing some of the atmospheric, and also that's at the terminator line, right? So that's between day and night cycles. There's a bunch of, the cold is mixing, cold, it's mixing with the warm.
Okay.
Yeah.
Okay.
That is pretty interesting.
Yeah, that is really interesting. It's a very interesting planet.
It is. So this is a map of Halley's Comet, based off the television images.
Based off what the TV said.
Yeah. You trust everything you see on TV? Well, in this case, yeah, it's a Soviet TV.
Yeah.
Oh no.
Soviet TV.
So those are
Can't trust nothing from them commies.
Yeah. So these are actually the first images of Halley's Comet, up close. You saw them.
Yeah.
Aren't they great?
Yeah, they were high quality, HD, 4K,
Oh, yeah.
ray traced,
Yeah.
RTX on.
Yeah. So it's about a 15-kilometer potato. As you can see, there's 2 lobes.
Yep.
So pretty much the most interesting thing that they found about that is that the geometric albedo, so that's how reflective it is 0.04. So the lower the number, the dimmer it is, the less it reflects light. So the moon, I think, is like 0.1.
Oh, okay. So it's like very dark.
It's very dark. The brightest is Enceladus at 0.99 because it's just ice.
Right. So it's just reflecting all the
Yeah.
light off of it, basically.
So pretty much the reason they think this is there is because of carbonaceous chondrites. A bunch of carbon. Basically, it's a carbon mud on the surface.
okay.
This is also one of the big inaccuracies of deep impact. The comet's too bright. When the spaceship flies up to it, yeah, it's too bright.
Interesting. So this should be like almost like a dark gray
Yeah.
or dark brown.
Yeah, but you try putting that on a movie. Where is it? Where's the comet?
Yeah. I think you gotta squint real hard. It's a very dark movie. It's got a lot of heavy themes.
Yeah. So here's what the infrared camera saw, and these are kind of the interesting results. So there's a few listed interesting bits of infrared data. Again, this is what I got from this. So there's no emission spectrum at 7.5 micrometers. So there's a weak one at 6.8, but that's likely due to a carbon-hydrogen combination or carbon grains. They thought there would be one, but it wasn't. Now this wavelength is from 3 to 5, so it's somewhere over here.
It's like 2.5 to 5.
Okay, this is the only legible graph I could find. All the others
The rest
didn't
were
make
too heavily pixelated.
Oh, the others didn't make any sense. This one makes sense,
okay.
right? Intensity, there. That's water. That might be ice. There's stuff. And there's other stuff.
There's other stuff. Yeah, there's more stuff. There's a lot of stuff there.
Yeah. 2. Absence of narrow molecular features from 6 to 11 micrometers. This is probably because of the limitations of the instrument and because the sun is there messing with it.
Oh, okay.
2. There's a strong silicate emission at 9 and 11.2 micrometers, indicating that there's olivines, right? But not in the same crystal structure as interstellar dust.
Ooh.
So they're different.
Okay, so it's not just interstellar dust. It's like, it didn't just like...
Yeah.
It's in the...
So something's going
That's
on,
weird.
right? Some chemistry happening.
Yeah.
The main discoveries are water production. A carbon
Making water.
Yeah, a carbon dioxide spectrum. So it's giving off carbon dioxide, which is the first we've ever discovered that. Strong broad emission of carbon-hydrogen bonds. The presence of formaldehyde. So that's the stuff that they use to embalm dead bodies.
Oh.
Yeah. It's also...
Oh, for Mark Twain.
Yeah, that's it. That's his body right there.
Yeah.
And marginal features like oxygen, carbon, sulfur, and carbon-nitrogen bonds.
Cool.
Yeah. Again, if you're a chemist, this is really interesting.
Yeah, or a geologist, or like one of those science people.
Yeah. I'm an engineer. How much does the dust do? Oh, so this is the magnetic field. Again, I just kind of breezed through this because I don't understand any of it. So these are the magnetic field vectors as it did the comet flyby. As you can see.
Yeah.
Yep. This is the real thing. This is what we really care about. Dust.
The dust
particles.
Yes!
So this is Vega 1. This is Vega 2. Because you can see the distance from it, right? So you'll notice.
Right.
It gets hit by a lot of dust the closer it gets.
Yeah, wow. In a dust-emitting object, you're going to get more dust?
Yeah, science.
Closer again? Wow.
Yep. So that's the dust. So here's some other results.
Cool.
Important ones. The big one is for Giotto, because Giotto did a close encounter with Halley's Comet on March 11th, 1986. Because of Vega, it was able to do better navigation on its approach. At an approach of 560 kilometers, about 345 miles.
That's pretty close compared to 8,000. What is it? 8,000 miles?
8,000 kilometers, so it's like 5,000 miles. Yeah.
5,000 miles. Yeah. Okay.
No,
that's a big difference.
Noticeable difference. So this also helps plan for future missions. There have been studies for balloon missions to Venus. None of them have ever materialized, but there have been proposals for them. So this is actually JPL built this in 2004, their own version of the balloons. There was the NASA proposal called Havoc which would use blimps to do human exploration of Venus.
Ooh, that sounds pretty cool.
It's pretty cool, but very risky from a crew risk perspective.
Yeah, you're putting people onto a pressure cooker. Probably not the best idea.
It relies on balloons deploying at a certain altitude.
Yeah. So everything has to go right.
Yeah. A high-risk mission compared to, Mars.
Yeah, maybe we shouldn't put people on Venus.
Not yet, at least.
Yeah. Yeah, not yet at least. Not until we perfect our balloon technology.
Yeah. So then we have Da Vinci Plus, which is an upcoming mission. Will be the first mission since Vega to enter and record data on the Venusian atmosphere. During its 63-minute flight, it will examine the atmosphere and its dynamics, as well as return images from the surface, which will be the first since 1983.
1983?
Yeah.
Wasn't this in the 1985, 1986?
This didn't take pictures.
Oh, okay.
Yeah.
Right. So that's 40 years
Yeah.
since we've taken images on Venus.
Not much has probably changed, I'm willing to bet.
Yeah.
Just saying, no offense to Venus, but...
In terms of activity, it's pretty dull,
Yeah.
pretty boring. Not a whole lot going on there.
Yeah, so Da Vinci and I've got Veritas are the missions that are going to Venus in the late 2020s.
Okay.
Yeah.
That'll be pretty exciting.
At the expense of an Io mission and I think a Neptune orbiter.
Oh, okay. Let's, that kind of sucks.
Yeah, well... Because this announcement happened around... Because remember when you heard about, like, the phosphine in Venus's atmosphere observations, which turned out to be probably just noise?
Yeah.
Probably around the same time. So that might have influenced it.
Oh.
Yeah. But, mission to Venus, because right now, active missions orbiting Venus, there's the Japanese one.
Mm-hmm.
That's it.
Oh, okay.
I know India's planning a Venus mission in, like, 2030. The Russians are doing another Vendra mission, which... Good luck, guys. Then we got these.
Best of luck.
Yeah. And the Chinese might be doing one coming up. I know. Rocket Lab's going to do one next year. I think.
Okay.
Or 2025.
Oh, really?
Yeah.
Oh.
Might be interesting.
Yeah.
So this is Vega 1 and Vega 2. This is another picture of the spacecraft. So you can see them working on the TV camera and the spectrometer, and then this guy's just reading the newspaper, I guess.
I cannot read it. It is in English
Yeah.
for no reason.
Yeah. Vasily, why is this in English? Oh, no. So that's Vega.
Oh, wait. It would be French, right?
Yeah.
Because the
it'd
French.
be really-
Why is it in French?
Yeah. That'd be a really conservative in English. Guys,
Yeah.
something's wrong.
Why did the French write this in English for Russians? I don't get it.
Oh, no. So that's Vega. What did we learn today?
I learned that if at first you don't succeed, try again.
Yeah. Again, the Soviets launched 29 missions to Venus. 14 of them worked.
50% success rate.
The United
That's good
States
enough.
launched, in that time period, 7 missions to Venus. 6 of them worked.
Yeah, but still, 6 is less than 14. So
That's true.
Who are the real losers here?
Right?
Yeah. I also learned that Venus does have life in the form of a bird,
Which they killed.
which they killed. Vega 1 killed on the way down.
Yep.
And in turn destroyed the mission.
Yep. Yeah, that's why they guys launched them in pairs. If one of them doesn't work, the other one might.
Yeah, if one hits a bird, the other might not.
Yeah. That's the
I
thing.
learned that Venus is a very interesting planet in terms of its chemistry and volcanism, surface, and all for the science and nerd stuff.
Yeah.
And the atmosphere is just doing a bunch of whack, goofy stuff.
Yeah.
Yeah.
That's about it, really. For future episodes, I'm going to focus more on American missions. Primarily because it's easier to get information on them.
Yeah, it's not locked up in a military, abandoned military warehouse.
Yeah, it's not the same
Somewhere.
warehouse as Buran, which collapsed.
Yeah.
And a cassette player that's only the one type of cassette player that was built in 1982 by the Soviets for some reason.
And he can't play it.
Yeah, it doesn't work because they use it as a heater instead for some reason.
Yeah.
Yeah, that's Vega 1 and 2. French balloons on Venus, which is really cool. I want to emphasize how
Yeah.
cool that is.
That is awesome. And they booked it
Oh, yeah.
across the planet.
Yeah. That's what makes it really interesting. There's balloons, and no one really talks about that.
Yeah, no. It's like, oh, we put a helicopter on Mars. Oh, yeah, well, guess what? We put balloons on
balloons.
Venus. We put 2 balloons on Venus in the 80s.
Yeah. Yep, so that's Vega. On the next episode, we're going to Jupiter to get more stupider.
So first we went to Venus to get a bigger understanding of the planet as a whole.
We penetrated
And
the
now we're going
atmosphere.
Yeah, exactly. And now we're going to the monolith.
Yeah, there's a signal on the moon. We dug it up, Clavius, Tycho crater, and now we got to go. And this is our mission. Looks a bit different than the Discovery from 2001.
Yeah, it's a little smaller.
It's quite smaller. What do you think this is about? What do you think this shuttle mission? I want to be very clear. We're talking about the shuttle mission first.
Yeah.
What do you think it's about?
I think it's about a shuttle mission, maybe the deployment of the Discovery 1.
Of course. Yep. That's yeah. That's what it is.
Yeah.
Okay, comrade. I think we're good on this one. For some custodial things, obviously, I'm gonna upload these at different times on Monday. We upload it at 4 Central now because apparently uploading at 8 a.m. on Mondays means no one watches it. Remember to like, comment, subscribe, share, evangelize, go door to door, that sort of thing.
Yeah, spread these out, like print these out in like little cards, like 3.5 by 5 cards, and
Punch
then
cards.
just and then just start staple them together and just start handing them out. Put them in like your local gas station bathrooms, porta potties you might find.
Yeah.
Throw them over the fences for construction.
Yeah.
For new buildings, and like have the construction workers read them.
Yeah.
Oh, spread them out.
Oh, the other thing that we're to talk about after this is we're trying to figure out where to upload this for other podcasting sites like Podbean, SoundCloud. I'm a rapper there. My rap name is Yo-Yo D-Spin. I thought of that like 10.
What?
I thought of that like 10 years ago. That's my rap name.
Yo-Yo D's.
Yeah. That's how you just. Okay, we'll talk about that some other time. But yeah, so if you have any sites that do podcasting that we could use and upload these things to, obviously not the visual side, but the audio side, feel free to recommend those. My ultimate goal is to send the podcast out as myth and legend, but we're building to that.
Yeah, we can't exactly afford to do the whole Homer thing of going from house to house and spreading the good word of end of mission. So yeah, we have to go to other places.
Yeah.
Expand.
Yeah.
Grow.
Yeah.
Expand. Explode.
Yeah, like the Courage the Cowardly Dog episode. I know that's where we were going. I stopped you.
Yeah.
That might scare some
Dang it.
people. Apparently that show
Yeah.
scared people. I don't know. I loved it.
Yeah, it was a great show.
Yeah, it was cool. Return the slab.
Fantastic.
That's what we're doing with this mission. We're returning the slab. There's a slab on the spacecraft.
Yeah, you see the memes of that where it's like return the slab and it's like sand getting into places where it shouldn't be.
Yeah, that's what I think we're doing. Returning the monolith.
Yeah, return the slab. We got it. Yeah.
Yeah. Okay,
Return to the monolith.
let's end this now.
All right. Rest in peace, Mark Twain. This has been End of Mission.